So the idea with this series of lectures is that it's meant to be about Nakajima's, it's meant to be based on Nakajima's famous book, Lectures on Hilbert Schemes of Points on Surfaces, which you, I think, can find electronic versions of online, although they may be not quite exactly the same as the published version. And this book has a lot of things in it, and it's perhaps written a bit tersely for PhD students. So the idea was to pick out some interesting parts of this, parts that are particularly interesting for those whose focus is on representation theory, and hopefully explain them in a way that will be a bit more accessible. But I wanted to start with the actual main concept, which is the concept of Hilbert scheme. So this is not, or for, at least for us, it's not going to be quite as scary as it sounds, because actually, to be honest, in the cases that we'll look at, the Hilbert schemes are actually Hilbert varieties. So things are a little bit more easy to comprehend than they are in general, maybe. So I'll start off with an introduction. So let X be a variety, and I'll only ever consider varieties over C. And probably for some of the things I'm going to say, you would want to make some slight further assumptions on X, but I won't go into that now because we're very soon going to specialize to the case where X is a surface. Then the concept of Hilbert scheme needs to be contrasted with the concept of symmetric powers. So I'll talk about that first. So the nth symmetric power of X, which Nakajima writes as SNX, which I'm not crazy about because that's the same notation as for the symmetric power of a vector space in multilinear algebra. And, you know, well, anyway, I would rather there was some distinction, but a bit better follow his notation, because we should probably stick as close to the notation in the book as possible. This is, by definition, it's a quotient of the Cartesian power. So if you take the product of n copies of X, and then take the quotient of that by the action of the symmetric group, Sn. So the symmetric group is just acting by permuting the copies. Then you get the nth symmetric power. So what this means is that if you want to know what a point of this symmetric power is, I should maybe make some general disclaimer that when I say point of a variety, I always mean point over C. And Nakajima in most of the book doesn't make any very careful distinctions between a variety and its set of points over C. So you need to worry about that at some points, but I won't stress it very often. So a point of this symmetric power then is an SN orbit on the Cartesian. Whoops, sorry. An SN orbit on this Cartesian power. So what that means is an unordered n tuple of points of X. And repetition is allowed here. So you could say it like that, or you could say that it's a multiset of elements of X. of size n, where you count the size of a multiset counts multiplicities if you have elements of x repeated. Or in algebraic geometry terms, this is usually called a zero-dimensional cycle. Because they're usually written as a formal sum of points of x. So you put square brackets around the points of x to be able to write them in linear combinations, and the coefficients are meant to be some non-negative integers, almost all zero. And for a cycle written like that, the word that's used is length rather than size. So saying that this is of length n is saying that the sum of these non-negative integer coefficients is n. These nx are in n. So it's some formal sum of points of the variety x. Okay, so in summary, a point in the nth symmetric power is a collection of n elements of x, except that you allow repetition. But it's different from just the ordinary Cartesian power because you don't care about order. So effectively, you just have a formal sum of points of x. So now, by contrast, the Nth Hilbert scheme which is in Nakajima's notation is written x with a superscript square brackets n. Well, it's meant to be a scheme. So the general definition of this scheme is something we won't really go very much into. But the property it's meant to have is that a point of the Hilbert scheme, again, a point, I mean a point over C, is meant to be a zero-dimensional closed subscheme of x of length n. So let's think about what this means. I mean, first of all, just on a naive level, this sounds pretty similar to what we had before when we had a collection of n points allowing repetition. Here, we've got a closed subscheme rather than a sub-multiset, but it is zero-dimensional, so it's meant to be just consisting of isolated points in some vague sense. And the length n part looks the same as before. But there's a difference. So to understand the difference, you have to unpack these algebraic geometry definitions a bit. So firstly, what do I mean by length? So if Z is a closed subscheme of X, then the length of Z is, by definition, the dimension of the, well, so here I guess I'm only saying things which make sense for zero-dimensional closed subschemes. The length is the dimension of the global sections of the structure sheaf of Z, and any such Z is supported at finitely many points, so you have a picture where here's X. This Z, this closed subscheme, whatever that means, it only lives at finitely many points of X, and this algebra of global sections of its structure sheaf is actually a direct product of its localizations at these various points. So this, the total length of this subscheme is actually just a sum of contributions at the various points. Sorry, this is a sum over X in the support of Z of the contributions from the localizations at these various points. So the picture is that you have this collection of points, and at each of these points you have a localization of your scheme there. And in particular, each of these individual local subschemes has a finite length, and the sum of all of the lengths is n. So I'm going to make this much more explicit in some affine examples in a minute. But what I want to point out now is just the relationship between this notion and the previous notion of nth symmetric power. So the point is that we have a map from the Hilbert scheme to the nth symmetric power, which Nakajima calls pi. Which takes one of these zero-dimensional closed subschemes and gives you what's called the cycle of Z, which is just the formal sum of the points in the support of Z, where you take each point as many times as this dimension of the localization of the structure sheaf of Z at that point. So this is the length of the localization of Z at X. So this map is actually a morphism. Well, at the moment we haven't defined any sort of scheme or variety structure on this Xn. It's just a set, but once we do define such structures, this will be a morphism, and it's called the Hilbert Scheme morphism. And in later lectures in the course, we'll hopefully see many of the interesting properties of this Hilbert Scheme morphism. This will be one of the main players.
Can I ask a technical question?
Yes, please do, Lin.
So will you still, so right now you've only defined the C points of Xn.
Yes.
And will you define so it's not enough for for a not necessarily reduced scheme. So I mean this information. So will you give other different definitions later, or?
Yes. So the main goal of today is to properly define the Hilbert scheme Xn in the special case where X is the affine plane. And that's already quite interesting and complicated enough. And then in later lectures, we'll see how to extend that definition to the case where X is an arbitrary surface. And we'll never in this course go into the definition of the scheme structure of the Hilbert scheme when X is an arbitrary variety.
So for example, in the easiest case, so that you were just talking about, will this Hilbert scheme be reduced?
Yes, in fact, yeah. I mean, in fact, in the case of surfaces, the Hilbert scheme we're talking about is itself an algebraic variety.
Right.
So it gives a misleading impression of the general situation, but yeah.
Thanks.
So yes, this is to come. So that's sort of the end of the introduction, in the sense that from now on, for the rest of today, I'm going to be looking at examples. I just wanted to introduce what is going to be the main players. So we're only going to really focus on the case where X is a surface, and I'll explain why that's the most natural case to look at in a minute. But when we do, we're going to be examining the various structures that the Hilbert scheme Xn has, and in particular how it relates to the symmetric power and the properties of this Hilbert morphism. These are going to be the sort of main focus. And as I said, the point of this is that it has various connections to representation theory, and those are going to be, I guess, our goals in understanding these algebraic geometry definitions, is to try and see what they tell us about representations of things. Okay, so I better go on to talk about examples and make this a bit more concrete. So in algebraic geometry, the first thing you should do when you see a definition about an arbitrary variety is to ask, what does this mean in the affine case? Because in the affine case, you should, in principle, be able to translate everything into properties or concepts about commutative rings. So in the affine case, we can do that sort of translation. So suppose X is an affine variety. And so then everything you say about X should have a corresponding translation into the language of commutative algebra, where you talk about the coordinate algebra of X. So I'll let A be the coordinate algebra. So when I talk about points of X in this case, in the case that that's an affine variety, you can think, instead of points, you can think of maximal ideals of A. So that's the first step in the dictionary, that to a point corresponds the ideal of the coordinate algebra, which consists of all polynomial functions on X which vanish at that point. And I also talked about, in the definition of the Hilbert scheme, I used the phrase closed subscheme. And closed subschemes of X correspond under this dictionary just to all ideals of A. So a point is a particular example of a closed subscheme, one of length 1. But in general, for any ideal of A, say I, you have a closed subscheme, which I might write Z brackets I for the closed subscheme of X corresponding to the ideal I. So I'm also going to need introduce the notion of the support of a subscheme, and the support of the subscheme that corresponds to the ideal I is just the set of points such that this maximal ideal contains the ideal I. So in other words, the set of points where all the polynomials, all the polynomial functions in the ideal I vanish. So this is a Zariski closed subset of X defined by the vanishing of these various polynomials in the ideal I. But the important thing to note about the definition of subscheme as opposed to subvariety is that different ideals can have the same radical, and therefore their subschemes can have the same support, but that doesn't mean that we still distinguish between those ideals. So if you have two different ideals whose radical is the same, then the support of those subschemes are the same, but because this the set of points where all the polynomials in the ideal vanish depends only on the radical of the ideal, but we distinguish the schemes in this case. So you have two different, different schemes with the same support, the same underlying closed subset of the variety. So this Zi is the affine scheme corresponding to the algebra, which is the quotient of A by the ideal I. And when I talked about zero-dimensional closed subschemes, that's equivalent to talking about finite-dimensional quotients of your original coordinate algebra. And in fact, the length that I spoke about is just the dimension of this quotient. So in the affine case, when X is an affine variety, you can translate everything I said into questions about the coordinate algebra A, as you would expect. And what you get is that the set of points of the Hilbert scheme, Xn, just corresponds in bijection to the set of ideals of the coordinate algebra which have codimension n.
Oh, sorry.
Yeah.
I have to ask a question about it. Might be very stupid, but or not. So in your remarks, so when I1 and I2 are two different distinct ideals, but with the same how do I say that?
The same radical, yeah.
Yeah, the same radical. So first, so the definition of Zi is just as a scheme, it's just a spec. Okay.
Yes, it's a spec of this of the quotient. Yeah.
Okay, cool. Yeah. Thanks.
Okay, so so this slide means that in the affine case, the points of the Hilbert scheme just correspond to ideals of codimension n in this algebra A. So this now means that we can easily work out a few examples, or easily think about a few examples, just by thinking about ideals in commutative rings. So let me move on to the first example, which is the affine line.
Sorry. Sorry. It's quite technical. So because I'm a little confused because X is a scheme, a fine variety. So right now you're using the language of varieties, and then for subschemes you switch to schemes. So by a variety you mean a scheme, a separated scheme, separated reduced scheme. scheme of finite type or something like that?
That's right, yeah.
Okay, thanks.
Yes, so actually maybe that's maybe it's worth pointing out. I mean, I would much prefer never to say the word scheme. I mean, because I guess as a young person, I was introduced to algebraic geometry through books that emphasize the context of varieties and linear algebraic groups. So you may wonder what parts of this require to talk about schemes, and it's interesting in a way because I started off letting X be a variety, and in fact, for almost the entire course, we're just going to talk about the case where X is a surface, so it's actually going to be a two-dimensional variety. And we're going to see later on that in that case, the Hilbert scheme, so-called, is actually also a variety. So it really could be called the Hilbert variety. So this is going to be a variety in the cases of interest. But this word scheme here, I can't get rid of. The whole point of the concept is that it's distinguishing between different closed subschemes with the same underlying closed subvariety. So the whole point is that when you're in this situation where you have two different ideals with the same radical, they give you the same closed subvariety of X, but they give you different closed subschemes of X. And the points of the Hilbert variety correspond to the subschemes of X.
Anthony, can I just ask, will the significance of subschemes be more than just a multiplicity thing, or will that kind of be?
Yeah, so that's another good question. So if it was just a multiplicity thing, then you would effectively have the symmetric power. So, so in the examples that we're about to see why it's why there's more information in the subscheme than just multiplicities. The point is that in the subscheme you have an algebra, a local algebra at each of these points, and local algebra is more than just its dimension. Yeah, so I mean that is the point that the examples will bring out, that you can have. Because you can have so many different local algebras of a given dimension, there's much more data in putting a local finite dimensional algebra at each of these points than just putting a number there. Yeah, thanks, Josh. Okay, so in fact, the first example won't show that because in the case of the affine line, or in fact any curve, things are a little bit disappointing. So let's take the most basic example of an affine variety, the affine line. So this is the affine variety whose coordinate algebra is the ring of polynomials in one variable. Nakajima uses the letter Z for the variable. So the points. No, sorry, I should call it lambda. The points in the affine line correspond to maximal ideals in this ring, and so the maximal ideal corresponding to lambda is just the polynomials of which lambda is a root. So this is, of course, the ideal generated by the polynomial z minus lambda. So that's the explicit description of maximal ideals in this case. But the disappointing thing about this example is that, of course, this is a principal ideal domain. So every ideal is generated by a single polynomial. And what's more, I'm working over an algebraically closed field. So every ideal is just the set of multiples of a single polynomial which you can factorize. So it has the form the multiples of z minus lambda 1, z minus lambda 2 to z minus lambda n. So I'll call this I, lambda 1, lambda 2 to lambda n. So, well, and if you take the ideal generated by a polynomial of degree n, then that's clearly of codimension n. So I could say, I could fix n from the start and say every codimension n ideal has this form for some particular choice of n complex numbers. And of course, repetition is allowed here. And order doesn't matter. So in this case, the ideal is actually completely determined by its support as a cycle. So the support, sorry, what am I trying to say? The cycle of the closed subscheme in this case is just this multiset with unordered multiset that we have here of these numbers lambda 1 up to lambda n. So in this case, the cycle determines the subscheme.
Well, just to confirm, the support is actually the radical, so it might be different, right?
Yes. So the support is the support is the set lambda 1 up to lambda n. Yeah. So that there can be some multiplicity. So the set may have fewer than n elements. Yeah. So the support just tells you the set. The cycle, by definition, tells you the multiset. It is actually the formal sum of these numbers, including the repetitions. And so, yeah, so the cycle does have enough information to determine the original ideal. It's just as the principal ideal generated by the polynomial who's with this factorization. Yeah, so Vidit's asked a question in the chat, which was the next thing I was going to say. So what this means is that in this case, the Hilbert-Schemes morphism is an isomorphism. So there's actually no difference in this case between the Nth Hilbert scheme and the Nth symmetric power.
Can I also interpret this fact as, so the reason for this fact is that there's only one possible direction for A1 at each point.
Yes, so that's it's a nice intuitive way to think about what's happening here, that you have this, this line. I don't know why I've drawn a curve since it's a line, but anyway, this one-dimensional thing. And if you were in the second symmetric power, for instance, you might have 2 points here. And in the second symmetric power, these 2 points could collide and become a single point with multiplicity 2. Because you're on a one-dimensional space, there's only one direction in which they can collide. Whereas if you're on a higher dimensional space, then there's points can collide in different ways. And the Hilbert scheme is keeping track of the directions in which they collide in a way that the symmetric power is not.
So which means that for like a smooth curve, so the same fact should also hold.
Yes. Yes, exactly. That is true. So the same holds. for any smooth curve X. Yeah, so which means one-dimensional variety. Yeah. So this is why the book is called Hilbert Schemes of Points on Surfaces, because surfaces is actually the first interesting case. So essentially from now on, we're going to assume that X is a surface. In fact, for the rest of today, X will be the affine plane. But
So for zero-dimensional subschemes of a smooth variety, it's they're determined just by multiplicity and direction in a tangent space?
no, I don't believe that's true either. I think there's more information in the actual local algebra that you can put at each point. But we may not see that in the A2 example. Yeah, so maybe that's a question I'll have to address in later things. So Lynn once put a comment on the chat as well.
I was just explaining why we could see directions in higher dimension, but it's not about Boris's last question. So. Okay,
all right. Yeah, so I think Lynn one's suggestion is going to be encompassed in the next example that I talk about.
I guess you can have not just directions, but Grassmannians of higher dimension, right?
Possibly. Sorry, Boris, I think I'm going to have to think about your question later. Okay, so now we come to the main topic for today, which is the case of the Hilbert scheme of points on the affine plane. So it's still an affine variety, and now our coordinate algebra is polynomials in two variables, which of course is not a principal ideal domain, so things can become much more interesting. So Nakajima calls the varieties, the variables Z1 and Z2, so I'll follow that. So to sum up what we've seen so far, this Hilbert scheme, Nth Hilbert scheme of A2, which we still haven't actually defined as a scheme or as a variety. All I've been talking about so far is its set of points. This set of points, so this is by definition the set of length n closed subschemes of A2, and translating into the terms of the coordinate algebra means codimension-n ideals. Of this polynomial ring in two variables. So this is an extremely concrete commutative algebra problem, which you could give in a first commutative algebra course. Try to classify all the finite codimension ideals of the ring of polynomials in two variables. So that's our question, how to describe this set. So let's start with the very easy cases. So n equals 0. Of course, there's only one codimension 0 ideal, which is the whole of the ring. So the 0th Hilbert scheme is not going to be interesting. This is a single point. When n equals 1, a codimension-n ideal of an algebra over an algebraically closed field like C is the same as a maximal ideal. Well, yeah, finitely generated algebra over an algebraically closed field. So we know what those are at least. Those are exactly the ideals that correspond to points in A2. So they're all of the form the maximal ideal corresponding to some point lambda mu. So it consists of all polynomials in two variables which vanish at this particular point. So this clearly has codimension-n, and the quotient is, to identify the quotient with C, you just take a polynomial and take its value at this point lambda mu. So points of the first Hilbert scheme are just the same as points of A2 itself. And in fact, once we give the proper algebraic geometry definition, this is just going to be isomorphic to A2 itself as a variety. So here you don't see any difference between the Hilbert scheme and the symmetric power, because of course S1 of A2 is also just A2.
Can I just remark that these first two cases, n equals 0, n equals 1, this is true for all varieties?
Yes, okay, thank you.
There's nothing special.
Yes, okay. In fact, yes, thank you. So the interest starts when we look at n equals 2. So we're thinking now about codimension-2 ideals inside the ring of polynomials in two variables. And we can use the facts we've seen before to help us think about this. In fact, for instance, the fact that there's a support, which is going to be either 2 points or a single point. So the easiest to think about is the case where the support is 2 points. Then the fact that these the support is these points means that the ideal is contained in the maximal ideals corresponding to these points. And if it's contained in both codimension-1 ideals, and this ideal has codimension-2, then in fact the ideal has to be the intersection of those two things. So in other words, it's just all the polynomial functions that vanish at these 2 points. That's one type of codimension-2 ideal where the support is 2 distinct points. The more interesting type is where the support is a single point. So in terms of ideals, that means that I is contained in the maximal ideal corresponding to lambda mu, and not contained in any other maximal ideals. So then maybe this should be an exercise, since we're getting close to the break. So the exercise should be that in this case, oops, I has to have the following form. So depending on the point you're at and an extra choice of a point in the projective line, so alpha and beta are the homogeneous coordinates for a point in P1. In other words, these are two numbers, not both zero, and you take them up to simultaneous scaling. So this should be the ideal generated by Z1 minus lambda squared, Z2 minus mu squared, and alpha times Z1 minus lambda plus beta times Z2 minus mu. So my hint for the exercise is that, well, firstly, it suffices to do this in the case where lambda and mu are both zero, which at least simplifies the notation, because you can just translate your variables Z1 and Z2. So you might as well just assume that the point you're talking about is the origin. And then you know that I is contained in the maximal ideal at the origin, which is the ideal generated by Z1 and Z2. And you know that it has codimension-2 in the whole thing. So if you think about the whole ring of polynomials in two variables and write down a basis, the monomial basis for it, so if you think of this as a picture of the whole polynomial ring, then inside here you have the maximal ideal corresponding to the origin, which is the span of all of those basis vectors except for one. And I is meant to be contained inside this blue part, and it's meant to be codimension-2 in the whole thing. So it has to be codimension-1 inside this maximal ideal. And so what I'm claiming here is that the form of I is that it has to include Z1 squared and Z2 squared. And of course it includes all the multiples of those. And it also has to include this last part here says that it has to include a linear combination of Z1 and Z2. It has to include a one-dimensional subspace of the two-dimensional space spanned by Z1 and Z2. So it sort of goes up in here and picks up some part of the span of Z1 and Z2 as well. So that's the sort of picture that this exercise is claiming I has to have.
And then since those zero subschemes are local, everything you're saying also works for any smooth varieties, right?
Yes. So the entire content of this slide would also be true for any smooth two-dimensional variety X. If you're talking about the second Hilbert scheme and subschemes that were supported at a single point.
This is confusingly sometimes called the punctual Hilbert scheme.
Yes, so it's punctual in the sense that it's related to points.
No, but it's points supported at a single point.
Oh, really?
Like the Hilbert scheme of points and the punctual Hilbert scheme I mean, this could be not totally consistent notation, but often when people talk about the punctual Hilbert scheme, they mean they're only looking at 0-dimensional schemes whose support is one fixed point.
Okay. So I've probably heard people use the phrase in that sense and completely misunderstood it. So thanks for pointing that out.
Yeah, it's confusing.
I have one question. So it's a notation question. So by codimension of ideal, do you mean co-height? Because there is for example,
No.
a maximal ideal has code. So in your notation, a maximal ideal has codimension 1. But
Yes.
usually,
That's because that's because C is algebraically closed. So
yeah, I mean because but usually so the notation I'm used to is so codimension means the height. And,
well, I guess
it's just a notation problem. It's nothing important. We just need to fix our convention.
yeah. Yeah. Okay. So I'm happy enough that the but they might differ if you were talking about a non-regular quotient of.
No, it's just a convention. There's nothing to do with the regular or non-regular, because so usually codimension means the height, because codimension is the the word codimension is for describing the subvariety. So the codimension of the subvariety.
Oh, right.
It's just so the notation you are using is exactly the inverse of the one I'm used to. So.
I see. Yes. So
Okay.
Kailan's put a comment in the chat, which is exactly right. That when I talk about codimension, I am purely talking about dimension as vector space. Yeah. So,
Yes. So,
yeah, so not the
that's why it's
coordination of the ring. Yeah.
Yeah, it's completely the inverse of the but so yeah, so I will use co-height for this, but anyway.
Okay.
Can I ask a question about the interpretation of the Hilbert scheme? Maybe it's a bit early to ask this, but will we see any sense in which like the Hilbert scheme is a solution to a universal problem of any kind?
Yes, hopefully. Probably not today, but yeah, probably next week. Yeah, so I mean, if you can get hold of Nakajima's notes, you'll see this on the first page.
Thanks. And does the notation have absolutely nothing to do with divided powers?
Yes, I think. Yeah, so there are some people. Let me go back. There are some alternative notations for this symmetric symmetric power. So quite often this is written as x as superscript parentheses n. And there I think that is intended to look like divided powers because you're taking the nth power and you're dividing by n factorial effectively. Except it's the symmetric group instead of the number n factorial. And so the notation for Hilbert scheme with the square brackets was probably, I think, chosen to contrast with this, with the round brackets in the symmetric.
This also looks like suspension, the nth suspension of x.
Yeah,
which is
yes. It's another reason why this notation that Nakajima uses is not so great. Yeah. Okay, so the exercise that I suggested here is not too hard, but you probably wouldn't want to classify codimension-n ideals in this ring of polynomials in two variables for general n just by actually thinking about what monomials the ideal may or may not contain, or how it would relate to these subspaces of the homogeneous subspaces or things like that. So we need a better way, and fortunately there is a better way. So I'm still just talking about the case of the affine plane. So these are ideals of the ring of polynomials in two variables. So there's this sort of elementary observation that you can recover an ideal of of a commutative ring like this from the quotient just regarded as a module over the ring of polynomials in two variables. Because the ideal is the annihilator of this module. So what that means is that the set of codimension-n ideals in this algebra is isomorphic to the set of isomorphism classes of n-dimensional cyclic modules for this algebra. So this is up to isomorphism. Isomorphism as modules over C, Z1, Z2. So cyclic here means generated by a single vector. Because every cyclic module over this ring is isomorphic to a module of the form where you just quotient out by a single ideal. Now, if you think of it in these more representation theoretic terms where you're classifying a particular kind of module over this ring up to isomorphism, then you sort of know what to do. For instance, it's a very familiar thing in this sort of representation theoretic classification to fix the underlying vector space. These n-dimensional cyclic modules, if you're classifying them up to isomorphism, you may as well say that the underlying vector space is Cn. And then what extra data is needed to make Cn into a module over this, a cyclic module over C, Z1, Z2. Well, you have first, you have to define the CZ1, Z2 module structure. So that means you need a way for Z1 to act and a way for Z2 to act. And so those are just going to act by linear transformations on Cn, or in other words, they're going to act by n matrices. So you need matrices B1 and B2, Nakajima calls them. And these are going to give the action of Z1 and Z2 on Cn. And since you want this to be a module for the ring of commuting polynomials in Z1 and Z2, you need these matrices to commute with each other. So the commutator has to be 0. So that's the data to turn Cn into a module over this ring CZ1, Z2. And then we here only care about the cyclic ones because we just want the quotients of CZ1, Z2 by ideals. So we also need a generator So the we're also going to throw in a vector which generates Cn over these matrices, these linear transformations B1 and B2. So it generates Cn under the action of B1 and B2, i.e. what I mean by that is that there is no proper subspace S inside Cn such that V is contained in S and S is stable under the action of B1 and B2. Okay, so this is the data that, if starting with the vector space Cn, turns it into a cyclic module over the algebra of polynomials in two variables. You need two commuting matrices and a vector which generates the space under the action of those two matrices. So this second condition, as Nakajima points out in his first chapter, is it's known as stability. And that's for reasons to do with geometric invariant theory, which we'll get to later on. So you could equally well just call it the cyclic condition for now, but everyone calls it the stability condition. And we won't see the reason for that for a little while. So what that means is that it's natural then to consider, so I might leave those things visible. So then consider what Nakajima calls H tilde. So this is the set of all triples, B1, B2, and V in the vector space, the direct sum of two copies of n by n matrices and Cn, such that B1 and B2 commute, and you have the stability condition. And elements of H tilde then define n-dimensional cyclic modules over C, Z1, Z2. And so they define codimension-n ideals inside C, Z1, Z2. So for a point in here, this defines the codimension-n ideal, which is the annihilator of Cn with Z1 acting by B1, Z2 acting by B2. So the annihilator in the ring, C, Z1, Z2, I mean, which is exactly the polynomials which vanish when you interpret them as polynomials of these two matrices. When you plug in the two matrices for the variables, and this is now an n by n matrix, it's the zero matrix. Okay, now the other question is, when do two elements of H tilde define isomorphic cyclic CZ1, Z2 modules. And the answer is exactly when there's an isomorphism from one module to the other. So since the underlying vector space is Cn, that isomorphism is going to be in particular an invertible linear map on linear transformation of Cn, so an element of GLNC. To define an isomorphism between the module structure defined by B1, B2, and the one defined by B1 prime and B2 prime and V prime, it has to be such that it conjugates this element of GLNC, conjugates B1 to B1 prime, conjugates B2 to B2 prime, and it maps V to V prime. So in fact, we have an action of the group GLNC on the set H tilde given by the left-hand sides of these equations. And what we're saying now is that the set of points of the Nth Hilbert scheme of A2 is in bijection with the set of GLNC orbits in the set H tilde. So this has translated the problem of describing the points of this Hilbert scheme into a problem of linear algebra, where you're describing instead triples of two matrices and a vector, satisfying some conditions, up to a natural action of the group GLNC.
Sorry, Anthony, I'm confused a bit. Why doesn't this ideal seem not to depend on V?
Yeah, that's a very good question. I was sort of expecting that someone would ask that because it is rather glaring. So yes, as Boris points out, there's no occurrence of the vector V in this definition here. And in fact, everything I've said up to this point would be true if instead of adding the data of V, I just made it a condition on B1 and B2 that there exists a vector V such that this is true. I didn't really, all I needed here was the property of the module being cyclic. So I could have just said that B1 and B2 satisfy the condition that there exists such a vector V and left V out of the data. Of course, you can easily see that if you have a cyclic module like this, then its generator is uniquely determined up to scalar. So the property that there exists such a vector is not very far from actually choosing the data of such a vector. And the data of such a vector is going to make a critical difference in what comes next. That's why the vector gets thrown in, even though it's so far everything could be said without it. Okay, so I might actually illustrate that by bringing forward yeah, okay, so I think this is worth pointing out. So why do we actually it's because of this nice proposition that the action of GLNC on H tilde is free. So free means that no non-identity element of the group fixes anything. So suppose that you have an element of H tilde which is fixed by some element of the group. Then so what that means is that G commutes with B1 and B2, and G fixes the vector V. But if that's the case, then if you let the S be the one eigenspace of G, since G commutes with B1 and B2 stabilize its eigenspaces. So this is stable under B1 and B2, and it contains V. So by the stability condition, S is the whole of Cn.
Anthony, can I just ask a question?
Yeah.
Above the proposition, you have this left-right arrow with GLNC and H tilde. Will the scheme structure on the left-hand side end up being the same as the scheme structure on the right-hand side?
Yes. So in fact, you've spoiled the punchline a little bit, but what I was actually going to propose, what Nakajima proposes, is to actually define the Nth Hilbert scheme to be a suitable algebraic geometric defined quotient like this on the right-hand side, and therefore make this true by definition. So yes. So the one eigenspace of G is the whole of Cn. So that means that G is the identity. So the only group element that fixes everything is the identity, which is what it means to be a free action.
So for n is equal to 2, V is going to define the element of P1, right?
No. No. Okay. So let me answer that by looking at again at the case n equals 2. Okay, so maybe just make let me make a general comment first, which is that since B1 and B2 commute with each other, they can be simultaneously triangularized. So after conjugating by some element of GLNC, we can arrange that B1 is upper triangular with some diagonal entries lambda 1. And B2 is upper triangular with some diagonal entries mu n, some stuff above the diagonal, and 0 down here. So this will have to be another exercise. that the cycle of the corresponding points of the Hilbert scheme then is obtained by just reading off the diagonal entries as pairs. So you have the point lambda1 mu1, and you have the point lambda2 mu2. And lambda nu, mu nu, and so on. So if you unravel all the definitions, this is not too hard to see. That tells you sort of what the Hilbert-Chow morphism looks like in these terms. Once you have your triple B1, B2, V, whose GLNC orbit is giving you your point in the Hilbert scheme, if you then want to map it to the symmetric power, then all you're doing is reading off the spectral information, just the eigenvalues of the matrices B1 and B2, once you've simultaneously triangularized them. And so the extra information that the Hilbert scheme captures that the symmetric power does not is all the things that can happen above the diagonal. So all sorts of information about Jordan blocks and other types of things. I mean, when you're classifying pairs of commuting matrices like this, then it's more complicated than just the Jordan form. I mean, you can put one of them in Jordan form, but then the other one might not be upper triangular, so you don't necessarily just want to think about Jordan forms.
Sorry, excuse me.
Yes.
I was distracted for a little bit. So have we a secret? So in the proposition, have we secretly used the lunar slice theorem?
No, no. This proposition is just meant to be a statement about sets. I mean,
okay, but we want to take quotient, and we need.
Yes.
Yeah. So I just gave some talks on equivalent direct category, and when I said free, it means something different.
Yes, you're right. So that
so if anyone attended to my talk, then our free means something different.
Yes. So I mean, so I haven't even put a variety structure on H tilde yet, although you can probably imagine that one. And the action of GLNC on H tilde is free in that more sophisticated algebraic geometry sense as well. But yeah,
that's lunar slice theorem, right?
Yes, I guess you would need, yeah, for the properness, you would need to appeal to lunar slice theorem. Yeah. Okay, what's the best thing to say next? So just continuing on to address Boris's question about the n equals 2 case. So for n equals 2, if you take B1 to be lambda 0 beta, and B2 to be mu 0, I guess it's minus alpha, and V can be the vector 0, 1. So if alpha and beta are not both 0, then this vector will generate the whole of C2 under these two matrices. And this choice corresponds to the ideal that I had before that was called I lambda mu alpha beta. So Boris, your question was about what where in this picture you see this direction part, the given by the point in P1. And so it's not so much in the vector as it is in the stuff above the diagonal in the matrices.
Yeah, I see. Thank you.
So another nice little exercise, which I won't have time to go through, is to use this point of view to complete the n equals 3 case. I.e. classify codimension 3 ideals. So the only interesting part, so an easier version of the exercise, which actually captures all the interesting bit, is to just assume that B1 and B2 are nilpotent. So in other words, there you're just describing what Emily said was called the punctual Hilbert scheme, where you're just looking at, so this is just describe the fiber of the Hilbert-Chow morphism over the cycle where you have the identity 3 times. So according to the principle I've got here, that corresponds to taking nilpotent matrices where the diagonal, upper triangular, where the diagonal entries are 0. And so it's not too hard then to classify all of those up to the conjugation action of GL3C, and thus describe all the codimension 3 ideals which lie above the identity.
And then notice that the other cases we've basically already done. If the 3 points are distinct, it will be easy. And if there's only 2 points in the support, one of them will have multiplicity 2, and that will be the case that we just did. And one of them will be multiplicity 1. So it kind of factorizes.
Yeah. Yeah, thanks, Emily. So I shouldn't have, maybe it was silly to say this was the easier version. So, I mean, essentially it reduces to this case. Okay, so that exercise is meant to illustrate that this point of view is useful in terms of describing the points of the Hilbert scheme, because at least, well, when I was trying to think about it, I didn't find it easy to directly classify codimension 3 ideals. But knowing about Jordan form of 3 by 3 nilpotent matrices, I did find it relatively easy to classify triples B1, B2, V up to action of GL3. But the other main point about this this change of viewpoint is, as we already saw, that it enables us to say what algebraic geometric structure we want on this Hilbert scheme, because we want this to be an isomorphism of varieties, not just a bijection of sets. So Nakajima proposes to actually use the known ways of defining variety structures on quotients like this to define the Hilbert scheme A2n. So the way that works is what I want to talk about for the rest of the lecture.
You say, why is it the right way to do it?
Well, yeah, so ultimately you can only be convinced that it's the right definition when you know that it represents the right functor. So there is a completely general definition of what functor the Hilbert scheme ought to represent. And so in Nakajima's approach, you define the Hilbert scheme of A2 to be this quotient, if you already know how to define a variety structure on a quotient like that. And then you show that the functor that it represents is the right one. So, so it deserves to be called the Hilbert scheme. So I'm not going to get to that latter part today, but I might be able to talk about that in the next lecture. Okay, so we want, so I just want to explain for the benefit of those who are new to this, how you think of a quotient like this as a variety. I mean, first of all, we need to think of H tilde as a variety. That part's not so hard. So what I want to head to is the variety structure on this quotient of the GLNC action on H tilde. So firstly, we've got some vector space that we're working in, and I think I'll need a notation for it, so let me call it M. So this is the vector space of triples B1, B2, and V. So a point here is a triple of two matrices and a vector with no conditions. And so the first condition we imposed on this was that B1 and B2 commuted. So that's pretty obviously a closed condition. We can express it like this, that we have a regular map or a morphism, I'll call it psi, from M to n by n matrices, which takes a triple to the commutator of B1 and B2. And clearly this is a morphism of varieties. These are both affine spaces here, the domain and codomain. So all I'm saying is that this is a polynomial map. Clearly the entries of the matrix, which is the commutator of B1 and B2, are polynomial functions of the entries of B1 and B2. In fact, they're degree 2 homogeneous functions of the entries of B1 and B2. So if you just impose the condition that B1 and B2 commute, I'll call that just psi inverse of 0. That is an affine variety. So it's a Zariski closed subset of this vector space M. It's called the commuting. Oh, well, if you didn't have the vector here, it would be called the commuting variety. Now, so we've seen that, well, GLNC acts on M, and this is clearly GLNC stable. The condition that B1 and B2 commute is left unchanged if you conjugate both B1 and B2. So maybe I should have said that the map psi, or the entries of the map psi are all invariant functions on M for the action of GLNC. So we have an action of GLNC on this affine variety as well. And we could form a quotient of this affine variety by GLNC in the sense of algebraic geometry, which is usually written with a double quotient sign. When you do that, all you're doing is taking another affine variety, the one whose coordinate algebra is the GLNC invariant functions on this affine variety. So you have a coordinate algebra of psi inverse of 0. This is some quotient of the algebra of polynomial functions on the whole vector space M. And inside there, you could look at the ones which are GLNC invariant. And by general theorems, that forms a finitely generated subalgebra of this. So it corresponds to some affine variety. But actually, this is not what we want to do, because points of a quotient defined in this sort of way don't correspond to GLNC orbits in here. They correspond to closed GLNC orbits in here, just the orbits which are closed for the Zariski topology. This is part of the general problem of taking quotients in algebraic geometry, that you don't have enough functions to distinguish between all the orbits, because all you have are the polynomial functions. So you can't distinguish between two orbits if their closures intersect. And in fact, the orbits we want are the GLNC orbits in H tilde, which is a subset of psi inverse of 0. And in fact, they're definitely not closed. Because if you think about it, a closed orbit would have to have the vector part being 0, because you've got the action of scalars in particular, which will scale the vector. If you act by the scalar matrices in GLNC, it leaves B1 and B2 unchanged and scales the vector. So you always have the triple where the vector is 0 in the closure. Okay, so this quotient is, this particular quotient, the affine variety with this particular coordinate algebra of GLNC invariant functions on this psi inverse of 0 is not what we want. But there is a, well, there's a well-known body of theory that applies to situations like this. So what I'm saying here is part of a much more general story. It's nice to go through it in a fairly concrete situation like this. So what we actually want to look at is H tilde. Now, H tilde is an open subset of psi inverse of 0. The stability condition is an open condition in the Zariski topology. So I'll explain why that is. So as an open subset of an affine variety, that means that this has the structure of a quasi-affine variety. So to see that it's open, you just have to rephrase the stability condition in a suitable way. Open subsets are meant to be given by conditions that some polynomials don't vanish. So how can we rephrase stability in those terms? If you have a point B1, B2, V in this affine variety, so B1 and B2 commute with each other, what's the condition for it to belong to our set H tilde? So the condition was that that V generates the whole of Cn under the action of B1 and B2. So that means the dimension of the span of the following collection of vectors, V, B1, V, B2, V, B1 squared V, B1, B2, V, B2 squared V, etc. All polynomials in B1 and B2 applied to V, that's meant to be the whole of Cn. So the dimension of that is meant to be n. And even though we have an infinite list of vectors here, if the dimension of the span is meant to be n, that means there's some finite subset of n of them which span the whole thing. So that's equivalent to saying that there are n of these vectors such that if you put them together in an n by n matrix, it has determinant non-zero. So the determinant of an n by n matrix formed by n of these vectors is non-zero for some v1, v2 up to vn in this list of vectors here. So this, in fact, explicitly writes H tilde as an open subset because belonging to H tilde is equivalent to a disjunction of various open conditions, various polynomial inequations. And the reason I've written it out in this gory detail is because it's important to point out that each of these individual open subsets is affine because it's a principal thing given by the non-vanishing of a single polynomial. So H tilde is the union of some principal open affine subsets of this affine variety. So the definition of principal open affine subset is these are the points in the affine variety where this regular function does not vanish. And this is for some f1, f2, and so forth. These are regular functions on psi inverse of 0. And they're not GLNC invariant. If you think about acting by a matrix in GLNC, so you just commute all the BIs and you act on the vectors. So what you end up with when you have a collection like this is that you just multiplied your matrix on the left on all of these things. So that won't leave this determinant unchanged. Instead, it will multiply it by the determinant of your matrix in GLNC. So these are GLNC semi-invariants. So if you act on a triple, you'll get the value multiplied by the determinant of G. However, being a semi-invariant is enough for the corresponding principal open affine subset to be stable under GLNC. It's enough for the condition that this polynomial doesn't vanish. To be preserved by GLNC. Another thing I should point out is that although I let this list go on in principle forever, so I had dots here, which in principle go on forever. And so there would, in principle, be infinitely many of these determinant functions you could write down. But actually, as we know from general theory, if you have a variety, it's if you've written it as the union of an infinite collection of opens, then it must actually be a the union of a finite collection, a finite subset of those opens. So actually this is, you only need finitely many of these.
Sorry, each of these components is affine abstractly, right?
Yeah, so each of these individual things is an affine variety, yes. So the and its coordinate algebra is just what you get by taking the coordinate algebra of the original affine variety and inverting Fi.
So Anthony, in principle, you get one of these FIs just by choosing a list of monomials in the B1J, B2,
Yep.
and then you have to look at the column of that matrix, and then you get a list of vectors. Is that correct?
Yeah. So you choose n of the expressions in this list here, and you make those the columns of an n by n matrix, and the Fi is the determinant of that n by n matrix. Okay, well, I'm almost out of time, so let me just cut to the chase. So then we can take GIT quotients of each of these principal open affines in the same way as before. And but now, because the action of GLNC is free, yes, actually it's true that you really want it to be free in the algebraic geometry sense of the word, not just the set theoretic notion of freeness that I proved before. And that follows from the lunar slice theorem, as Lin once said. These are now geometric quotients. So they get written with just a single quotient sign. I.e., the points are in bijection with the GLNC orbits in psi inverse 0 Fi. The orbits considered as subsets of this open set have to be closed because they're all maximal dimensions, since the stabilizers are all trivial. So all the orbits have the same dimension. And then you can glue these quotients of the individual affines together to get a variety, which is what the quotient we wanted. You know, a genuine geometric quotient where the points over C of the variety are the GLNC orbits in the set of points of H tilde. And Nakajima defines A2, the Nth Hilbert scheme of A2, to be this variety. Okay, so that's where I'll stop for today. And now what comes next is to actually use this this description to think more about the properties of this variety. In particular, we'll be able to show that it's smooth and that it has dimension 2n, and then to carry on to extend those results to other surfaces and see how what this tells us about the structure of the Hilbert-Scheme morphism in that case. So I guess that'll all be next week.